Here are two equilibrium problems for you to solve. Take a look at each one, solve it, and then compare it to the method that I used. Okay, for the first problem, I'm reading the equilibrium constant is very high for this chemical reaction, and I'm noticing that even when you take this alone, it's higher than these concentration values, which to me means that some sort of a quadratic assumption is not going to be valid, meaning I hope we can solve this problem exactly. And I'm reading that we have a chemical reaction here where everything's in equilibrium. I'm not going to omit anything. I'm going to remember to square this because the equilibrium constant is equal to products over reactants where the coefficients become exponents. And I notice it's in a half a liter flask, which means that the actual concentrations, remember square brackets means moles per liter, is going to be 2 for each of these. I see a temperature, but you always see a temperature and it doesn't change, so we can ignore it. And then we want to know the concentration of everything when equilibrium has been reached. Now this must have been set up so this can be solved exactly. So I am going to create a ice table and plug in my numbers. Good. I'm noticing it's going to be 2 liters. I'm noticing that this is not something where I can just ignore the changes because it's the changes would be significant since equilibrium is very high. There's my ice table setup, initial change in equilibrium, and they do tell you that initially it's 1 mole of each, so I must have, oh, I'm sorry, don't forget 2 moles of each, that's right, 2 molar, I should say, of each. And initially we have no product by definition, so there you go. Now I can say that these will each go down by a value of x. This will go up by a value of 2x, since for each of these that reacts, 2 of these form. And there's that. Do the math, and that's what you get here. And here we get those minus x's, which are so often ignored, but this time we don't have to. If they each go down by the same value, a nice thing happens mathematically. So I'm just now plugging into the equilibrium constant expression for concentration, hence the sub C. And there's everything plugged in, right? Our 3 bottom numbers. Now it's just a math problem. And it turns out since these are both the same thing, that's the same as 2 minus x squared. And can you see that it would be sweet to just take the square root of both sides because that'll clean that up so much? So we do. And it does clean it up a lot. I'll spare you describing every little detail to figure out what x is, but I'll show them here and here and there. And we get an exact value for x. Are we done? No. They want us to come up with the final values for everything, which means just put in that number for there, x, there, and there, and we'll solve. Now, a lot of students might just, write it down somewhere because it's all set up here. But if you have time, go ahead and write it down a second time and plug in exactly. So there's our values here for each. There's our final answers, and I think that is the answer to the questions. Those are the final concentrations at equilibrium. You can go ahead and check it to make sure it's right. That always gives you a wonderful feeling. I'd strongly recommend you do that for AP exams because your confidence will go up enormously when you do that. Okay, let's do another. Read the problem, solve it, compare it to what I did. Okay, good. I'm reading the equilibrium constant is very low, which is typical for situations where you can ignore that minus x value, right? And these are relatively low, so even if we take 100 times that value, it's still going to be less than this value. Some teachers call this the 100K is less than a approximation. It means that if we get minus x situations like these, we can ignore them. Now, not all classes, not all courses will allow you to do that, but some will, and in this case, we will. So what else? Let's read on. Oh, we got a temperature, and as usual, it just means that it's fixed and we can ignore it. It's really hot, by the way. And here's our initial concentration, so I'm thinking of putting them in an ice table, and they want the concentrations of everything when it's at equilibrium, just like before. So we're going to make that approximation when it comes in, but you could check that out later. Set up your ice table nice and carefully. This is always worthwhile. And that's the initial concentrations that are given. That's molar, so there's no trick like they had before. And the change is, well, that's going to go down by a value of x. That's going to go down by a value of x. That's going to go up by a value of x. I hope you're saying, no, no, that's right. This will go up by a value of 2x. For every one of those that goes away, two of those form. So don't mess that up. Now we can just do our little ledger accounting, which is easy, right? But in this case, since we're going to make that quadratic assumption, life gets so much easier. Since this is going down only by a tiny amount, we're going to assume it's nothing. That one, too. Now that solving it mathematically should be much easier. For some reason, I wrote it here just to be complete, but I'm going to just cross it out and do it again, right? So it's just, there it is. Now don't forget that this is coefficients over exponents. Put your parentheses in there. This is not 2x squared. This is 4x squared once you factor it out, right? So you're at this point now, and I think like before, I'll just show the work here because most students could follow this at this point. We want to isolate x. Oh, in fact, I didn't even show anything. So what would I be doing? I could take both sides, divide them by 4. I could turn that into a number. I could square root it, and I should have x there. And there is your value of x. Let's move that. So now we can plug in. Now, when I say plug in, I don't mean plug in completely because after all, this value is very low. And in fact, even if you took this number and subtracted almost nothing from it, well, you'd end up with just about the same number. And maybe that's convincing where you're like, oh, I can see why they do that quadratic approximation. I mean, look at how small that thing is. So we do that. We don't change it actually. But this one we can. We can go ahead and double this. Since it's plus 2x, and we have the answer to our question. These are the equilibrium concentrations of products and reactants. These are two more equilibrium problems.